introductions, we're talking about the differential equations. Differential equation is a mathematical statement that connects an unknown functions to its continuous rate of change. In a second order linear equations with a constant coefficient, the highest derivative is the second derivative, with which the fundamental allow us to model acceleration, resistance, and dynamic accumulation in real-time processes. For us, as a chemical engineering technology, which biotechnology students, these equations are crucial. We rely on them to simulate complex biological systems such as modeling transient biomass growth and substrate consumption inside a bioreactor, or tracking multi-compartment drug elimination profile in bioprocess pharmacokinetic. Based on instructions that given with a clear summary of the outline structure, our team will demonstrate how to solve this precise system using both chapters 3, homogeneous differential equations, and homogeneous mechanical application, and chapter 4, which is Laplace transforms.
Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. My name is Wanur Alisha Sofia binti Wanur Irman. Today, I will explain to you on method how to solve homogeneous differential equation. So, what is differential equation? Differential equation is a mathematical equation that relates a function with its derivatives, and the function usually represent physical quantities. Derivative represents the rates of its change, and the differential equation defines a relationship between the rate of change and the physical quantities. Okay, next, what is a homogeneous differential equation? It is a second-order linear differential equation when the right-hand side is 0. The solution is obtained by finding the auxiliary, which is the characteristic of the equation. The nature of the roots determine the form of the general solution. Next, I will explain about the application of homogeneous differential equation. First, we have mechanical vibration. It is used to model the motion of springs and oscillating system. For example, car suspension system and building vibration analysis during earthquake. Second, we have electrical circuits. It is used in ROC circuits to study the current and the voltage changes over time. And lastly, we have engineering and physics. It is usually used in structural analysis, control system, and signal processing. Next, I will explain to you on how to solve this homogeneous differential equation. We have 4 steps. First, from the equation a d square y over dx square plus b dy over dx plus cy equal to 0, we change it into the form of ar square plus br plus c equal to 0. Next, for steps 2, we need to find the root of the characteristic equation, which is the auxiliary. And next, step 3, we need to find the general solution according to the roots. It has 3 cases. First case is real and distinct, second case is real and equal, and the third case is a complex case. Step 4, if we are given any initial or boundary conditions, we can substitute it into the solution to obtain the value of the a and b. Next, I will talk to you about the 3 roots of the homogeneous differential equation. For the case 1, it is the distinct real root. It is when the b square is greater than the 4ac. Supposedly, the roots are r1 and r2. Then, the general equation is y is equal to c1 er1x plus c2 er2 2x. Next, for the equal real root, which is the b square is equal to 4ac, suppose that the roots are r1 and r2 real and equal such that r1 is equal to r2 is equal to r. Then, the general solution is y equal to, in a bracket, c1 plus c2x, close the bracket, e to the power of 2x. Next, we have the last case is the complex root, which is the b square is lesser than the 4ac. Supposedly, the roots are complex number, which is r is equal to alpha plus minus beta I. Then the general solution we can get is y is equal to e to the power of alpha x, in the bracket, c1 cos beta x plus c2 sin beta x. Okay, so next I will talk about the example for case 1. So the question asks us to solve d square y over dx square minus 5 dy dx plus 6y equal to 0. So first, you need to form the characteristic equation. And for the second step, you need to find the roots based on the characteristic equation. So you factor out the characteristic equation and you will get the r1 and r2. So next, you need to check the type of the roots. Using the discriminant b square minus 4ac, you substitute the value into the discriminant. Then you will get the type of root. For this case, the roots are distinct real roots. So lastly, write the general solution. For distinct root, as we know, the general solution is y equal to c1 er1x plus c2 er2x. So we need to substitute the r1 and r2 that we get from earlier. Example for the case 2 is we need to solve d square y over dx square minus 4 dy dx plus 4y equal to 0. So first, just like the case 1, you need to form the characteristic equation, which you got r square minus 4r plus 4 equal to 0. Second, you need to find the root. So based on the characteristic equation, you factorize the equation. Then you will get the r1 and r2. Next, you need to check the type of root. Using the same discriminant, which is b square minus 4ac, you substitute the value again and then you will get that the roots are repeated roots. So, to write the general solution, we know that y is equal to c1 plus c2x erx. So, we need to substitute the roots that we got earlier. So, we get y is equal to c1 plus c2x e2x. So, this equation, we multiply it by x, because if we simply wrote it as c1 e2x plus c2 e2x, both of them will be the same and not independent. Therefore, the second solution is multiplied by x to obtain the answer we get earlier. For case 3, we need to solve the d square y over dx square plus 4 dy dx plus 13y equal to 0. So, just like the other two cases, we need to form the characteristic equation. So, we get r square plus 4r plus 13 is equal to 0. So, next, based on that equation, you need to find the roots using the quadratic formula. So, the quadratic formula that we all know is x is equal to negative b plus minus square root b square minus 4ac over 2a. So, we substitute the value of a, b, and c in the quadratic formula. Then, we will get the root. You will realize realize that you get an imaginary root because when you square root the negative, you will get an imaginary answer. So after you obtain the answer, you need to check the type of the root using the same discriminant, which is b squared minus 4ac. Substitute the value, then you will get that the roots is the b squared is less than the 0, so the roots are a complex root. So next we'll need to identify the alpha and the beta for this question. So we need to compare we need to compare a plus minus alpha plus minus beta I with the r is equal to negative 2 plus minus 3i that we get earlier. So therefore we get alpha is equal to negative 2 and beta we get 3. So lastly, we can write the general solution for the complex root. As we know, y is equal to e alpha x in the bracket c1 cos beta x plus c2 sin beta x. So we just substitute the value of alpha and beta in the general solution. So we will get y is equal to e to the power of negative 2x in the bracket c1 cos 3x plus c2 sin 3x. That's all.
Hi everyone, I'm Day. I'm going to talk about non-homogeneous second order linear differential equation. So I'm going to start with the introduction first. A non-homogeneous second order differential equation is a differential equation that contains a non-zero function on the right hand side. Its general form is shown in the slide, as you can see, where the right hand side function is not equals to 0. The function is called the forcing term because it represents an external influence on the system. Non-homogeneous second-order linear differential equations are widely used to model real-world problems in physics, engineering, and other sciences. The method to solve the non-homogeneous second-order linear differential equation we separate into two parts. The first part is the complementary function. Given the standard equation as shown in the slide, then you temporarily set the function f to x equals to 0 and solve the characteristic quadratic equation, which is am squared plus bm plus c equals to 0. The roots m1, m2 determine the form of the complementary function. You can refer to the table given in the slide. And as for part 2, method of undetermined coefficient, once you have the complementary function, you look at the forcing function to guess the form of the particular integral. So there are three types of forcing functions. The first one is polynomial forcing function. If the function f to x is a polynomial of degree n, your guess for particular integral must include a complete polynomial of that same degree. For example, if the function f to x equals to 3x squared minus 1, the particular integral will be equals to ax squared plus bx plus c. If the function f to x equals to 5x, the particular integral will be equals to ax plus b. So the second types of forcing function is exponential forcing function. If the function f to x is an exponential, your guess retains the exact same exponent power. For example, if the function f to x equals to 4 exponential 3x, the particular integral will be equals to a exponential 3x. If the function f to x equals to negative exponential negative x, the particular integral will be equals to a exponential negative x. The third type of forcing function is trigonometric forcing function. If the function f to x contains a sine or cosine, your guess must include both sine and cosine terms of that same frequency. If the function f, for example, if the function f to x equals to sine 2x, the particular integral will be equals to a cos 2x plus b sin 2x. If the function f to x equals to cos 5x, the particular integral will be a cosine 5x plus b sin 5x. So an example question is solve d squared y dx squared plus 2 dy dx equals to x. Step 1. Find the complementary function. First, solve the homogeneous equation by setting the right side to 0, which is d squared y dx squared plus 2 dy dx equals to 0. Then we write the characteristic auxiliary equation, which is m squared plus 2m equals to 0. As you can see, they let m squared equals to d squared y dx squared and m equals to dy dx. After that, we factor out m and we get two roots, which is m1 equals to 0 and m2 equals to negative 2. Since the roots are real and distinct, our complementary function formula will be equals to c1 exponential m1x plus c2 exponential m2x. So we sub in the m1 equals to 0 and m2 equals to negative 2 in the complementary function, and we get c1 plus c2 exponential negative 2x. Step 2 is find a particular integral. The following function is the function f to x equals to x, which is a first degree polynomial. Normally for a first degree polynomial, your standard guess would be equals to ax plus b. However, look closely at the complementary function. It contains a constant term c1. Our guess for particular integral also contains a constant term b. Because they duplicate each other, they are not linearly independent. To fix this, we must multiply our entire guess by x. Then we get ax squared plus bx. Then we differentiate the guess. After that, we substitute into the original differential equation. And then we get 4ax plus 2a plus 2b equals to x. As for step 3, solve the coefficient a and b. Now compare the coefficient on the left side to the right side of the equation. For the x term, 4a equals to 1, so we get a equals to 1 over 4. For the constant terms, 2a plus 2b equals to 0, and then we substitute the a we obtained just now, which is 1 over 4, into the equation, and we get b equals to negative 1 over 4. After that, we substitute a and b back into the particular integral equation. Then we get 1 over 4x squared minus 1 over 4x. Lastly, we write the general solution. The final general solution is the sum of the complementary function and the particular function. So y equals to c1 plus c2 exponential negative 2x, then plus 1 over 4x squared minus 1 over 4x. Method to solve the variation of parameters. We first divide everything by a, so the d squared y dx squared coefficient is 1. After that, we find the complementary function, solve the homogeneous equation to get the complementary function equals to c1y1 plus c2y2. And then we need to identify two fundamental solutions, y1 and y2. So step 2, we calculate the Wronskian. The Wronskian determines if y1 and y2 are linearly independent. Set it up as a 2 times 2 determinant. Step 3, integrate to find u1 and u2. The variation of parameters assumes the particular solution looks like the particular integral equals to u1 y1 plus u2 y2, where the constants c1 c2 vary as functions. Find them using this integral as shown in the slides. You can see that. Then step 4, assemble the general solution. Plug u1 and u2 back into the particular integral equals to u1 y1 plus u2 y2, then combine everything, which is y equals to complementary function plus particular integral. Okay, this is used when the function f to x is ugly, like tangent x or secant x. Undetermined coefficient won't work. We use variation of parameters. The example question for variation of parameters is solve d square y dx square plus dy dx equals to tangent x. So step 1, the auxiliary equation is n squared plus 1 equals to 0. So the complementary function equals to c1 cos x plus c2 sin x. From this, we identify our two functions, y1 equals to cos x and y2 equals to sin x. Step 2, calculate the Wronskian. We need to find the derivative of y1 and y2 first. Then we use Wronskian to calculate and get cos x squared plus sin x squared equals to 1. Step 3, find u1 and u2. Our forcing function is function g2x equals to tangent x. So for u1 equals to negative integration in respect to x of sin x times tangent x over 1. And we get u1 equals to negative ln secant x plus tangent x and then plus sin x. For u2, it must be integration in respect to x of cos x times tangent x over 1. And we get u2 equals to negative cos x. Step 4, construct the particular integral and the general solution. Now substitute u1 and u2 into the particular integral, which is equals to u1 times y1 plus u2 times y2. Then we notice that sin x, cos x cancel out, and the final general solution, which is y equals to complementary function plus particular integral, and we get y equals to c1 cos x plus c2 sin x minus cos x ln secant x plus tangent x. This is the final answer. Mechanical engineer designing a suspension system for an off-road vehicle, or perhaps analyzing the vibration of a structural beam in a building, applying non-homogeneous second-order linear differential equation. Non-homogeneous second-order linear differential equation tells how system will behave under a continuous external force. There is an example given in the slide. Yeah, that's all.
Introduction of Laplace transform. Laplace transform is a mathematical technique used to convert a function of time ft into a function of a complex variable s. It transforms differential equation into algebraic equation, making them much easier to solve. The Laplace transform is of a function ft is defined as this equation. Symbol of Laplace transform is ft go to fs. The Laplace transform is a powerful mathematical tool that converts function from the time domain to ss domain, making it easier to solve differential equation and analyze engineering systems. It is one of the most important techniques in mathematics, engineering, and applied science. Next, we go to the properties of Laplace transform. There are three main types of Laplace transform. First, linearity, first shift theorem, and multiplication with Tn. Each type using a different formula to get function of complex variable s. This is the table of Laplace transform. First, linearity, first shift theorem, and multiplication with Tn. Every type of function use a different fs. First shift theorem also a different formula to get the Laplace transform. Multiplication with Tn also use a different. Next, we go to the example application to the Laplace transform. We go to the example question of each type. First, ft sama dengan 3. So 3 is a on the Laplace transform. So we can identify check on the table, we can use the Fs equal to A per S. So the final answer in this equation is 3 per S. Second equation is Ft equal to e power of negative 2t. So negative 2t is A. First step is check on the table on the Laplace transform what types we can use in this equation. So we can identify the Fs equal to A per S minus A. So the final answer in this equation is 1 over S plus 2. We go to the third equation. Ft equal to cos 4t. First step is a check on the table of the Laplace what can be used in this equation. So after identify, we can extract the data and replace it. So A is a 4. On the table we can use a S per S S power of 2 plus A power of 2. So the final answer in this equation is S over S power of 2 plus 4 plus 16. Next, equation 4. Ft equal SH 2 per 3t. Sin H means a hyperbolic. In this question, we can use the hyperbolic Laplace transform. So we can identify the A is 2 per 3 A. So the final answer is 6 over S 6 over 9S power of 2 minus 4. Next, we go to the hard equation, which is question 5. The question is find 3 cos H to t plus 2 sin H for t. In this for this equation, we can arrange the step. First, do one by one. Second, check on the table of the Laplace transform. 3, summarize all the parts. First, do one by one. We can separate the equation. So 3 cos H to t in one part and 2 sin H for t in part 2. Step 2, check on the table of Laplace transform. Laplace transform we can use is a cos hyperbolic at sin H at. Since the equation is both sin and cos is a hyperbolic. So after check on the table, we can identify the both part is a and we can include the A in the equation. So step 3 is a summarize all the parts. So the final answer in this equation is 3S over S power of 2 minus 4 plus 8 per S power of 2 minus 60. Next, we go to the equation 6. Ft per t power of 2 e power of 3t. In this equation, we can use the Laplace first shift theorem, which is we can use the Laplace first shift theorem and multiplication with tn. Check on the table. In this step, check on the table, which is we can use three Laplace transform. Next step is we can identify the A and include in the equation. So the final answer in this equation is 2 over S minus 3 power of 3. That's all.
Assalamualaikum and good afternoon. My name is Muhammad Haziq Azwan bin Hamidi. My matrix number is CN250456. Today I will talk about the inverse Laplace transform. first shift theorem and linearity. Okay, in the first slide we have the inverse Laplace. The inverse Laplace transform is the process of converting a frequency domain function fx back into the time domain function ft. Mathematically is represented as a Laplace fx equal to ft. To solve this efficiently without resorting the complex contour integration, we rely on a standard set of transform pair and property like partial fraction decomposition. Below we have the example question of the inverse Laplace. First we have the Laplace bracket 6 over s4 cross bracket equal to Laplace 3 fractional s4 cross bracket, and the answer is t power of 3. Okay, second slide we have the linear property of the inverse Laplace. In the linear property, we can split terms out and pull constant out just like in the standard integration. Linear property formula: Laplace fx plus bgx equal to a multiply Laplace fx plus b multiply Laplace gx. Okay. Below we have this example question for the linear property. Okay, first we want to find the inverse Laplace transformation. Looking at the denominator s power of 2 plus 4. Remind us of the standard form for sine and cosine. We have s2 plus w power of 2 at the bottom. However, the numerator has both an s term and a constant term mixed together. Using the linear property, we can split this into two separate fractions, one for the 3s term and one for the 8. And for the first time, we pull the constant 3 out for the front. This leaves us with the s per s power of 2 plus s2 power of 2, which perfectly match the standard cosine for the second term. The standard signs form require the constant in the numerator to be exactly which is 2. Since we have 8 in the numerator, we can factorize this as a 4 multiplied 2. We pull the 4 out to the front, leaving the required 2 inside the transform. Now the both terms properly match our standard table form. We take the inverse transform. The first term become the 3 cos 2t and the second term become the 4 sin 2t. Putting it all together, our final answer is 3 cos 2t plus 4 sin 2t. Lastly, we have the first shift property of the inverse Laplace. If your term as all shifted by constant s minus a is translated to multiply the domain time function by exponential e at t. If Laplace ft equal to fs, then Laplace f bracket s minus a equal to exponential a t ft. Below we have the example question for the first shift property. First, we identify the shift. The question below we have the 6 per in bracket s minus 1 power of 2 plus 4. Notice instead of clean s2 in the denominator, the s is packaged as the bracket s minus 1 plus bracket. This indicates that a frequency shift has occurred. According to the first shift property, a shift of ss in the s domain translates to multiply by exponential term e at t in the time domain. Here, our a equal to 1, so we can pull the shift complete out of the inverse transform operator by writing it as e1t or simply exponential t on the outside. Once we account for the shift, we replace every bracket s minus 1 left inside with the standard unshifted x. This simplifies of our remaining target down to finding the inverse Laplace of 6 per s power of 2 plus 4. Now we focus on the Laplace 6 per s power of 2 plus 4. The denominator is s power of 2 plus 2 power of 2, which points us toward the standard sign transform formula. However, the standard sign form required is numerator to wash sign v is 2 to balance if without changing the value of our expression. We can multiply and divide by 2 inside the operator. Rewriting the numerator 6 as a 6 per 2 multiply 2, which is 3 multiply 2. We keep the required 2 inside the transform and factor the constant 3 out to front alongside our expressionality terms. Lastly, that now our internal operator match the standard sign function perfectly, we can evaluate its Laplace 2 per s power of 2 plus 2 power of 2 becomes sin 2t. Combining everything together, our final result is a 3 expressionality sin 2t. That's all from me. Thank you.
So for a conclusion, second order linear differential equation with a constant coefficient can be solved using several complementary methods depending on the type of solutions. For homogeneous differential equation, the solution is obtained by forming and solving the characteristic equation to determine the complementary functions. For non-homogeneous differential equations, the complete solution consists of the complementary function and particular integral, which can be found using methods such as undetermined coefficients or variation of parameter. Meanwhile, the Laplace transforms provide a powerful alternative approach by converting differential equations into simpler algebraic equations in the S domains, making them easier to solve, especially for engineering and applied science problems. Together, this method form a comprehensive toolkit for analyzing and solving a wide range of mathematically and engineering systems involving second-order differential equations.